Hello and welcome back to Calculus 1. Tonight on the menu, the spicy chain rule. As I mentioned before, this is going to be your life in calculus. Pretty much every derivative starting tonight is going to be chain rule. Chain rule is a way to take the derivative of function composition. So this is nowhere on top, the bars. So we'll see. So use the chain rule to differentiate function composition. Please recall from pre-calculus 1, as we reviewed the last class, right at the end, that the function composition f composed with g is also written as f of g, like this, and means plug g of x for every x of f of x. So if I have that f of x is given as 3x squared minus 5 root x plus 6 over x, and g of x is 2x minus 1, the f of g of x would be 3g squared minus 5 root of g plus 6 over g of x, and then I replace each one of these g of x's with what it is. So f of g of x is 2x minus 1 squared minus 5 square root of 2x minus 1 plus 6 over 2x minus 1. The skill that we need is actually doing this backwards. This is exactly what you learned in your pre-calculus 1 class, or advanced algebra, or whatever it's called, when you took this in the past. You learned to take two functions or more and put them together into the new function. The skill that we need for this particular lecture and in the future of the course, and Calc 2 and 3, we need to be able to decompose, to do it backwards. So if I have that the function y is given to me as sine cubed of x, I need to be able to decompose this to understand that the outer function f of x is x cubed and the inner function g of x is sine x. Because if I check this, here's a check. If I want to compose f with g, I will put g of x cubed, and that's going to be sine x cubed, which we can write with the cube over there. So what we need to have as a skill is decomposing function composition, so that we see each one of the individual functions so that we can take derivatives. Let's decompose one more. Let's say we have y equals two x ln cubed x. Now, what I have here is something that we can rewrite using algebra as 2x open parenthesis ln x cubed. The 2x is multiplied into the second factor, which is ln x cubed, and this would be a product rule. Right? This would be a product rule because you have multiplication. But then you have this ln cubed part. And that's the part that would be chain because you have two functions. Again, so this piece would decompose into f of x equals x cubed again. Should have picked something else. And g of x equals ln x. And I'll just put here part of the product. Part of the product. So not every expression that you write immediately is entirely just chain rule. We'll see how these all combine together. Is the stream going? Is anyone watching? Because
I'm watching it. It's kind of blurred though. Is that how it's supposed to be?
No.
Or you could go on the side. Oh.
No, I see the red dot up there, and there's a red dot telling me there is some kind of problem, but there's not enough bandwidth for this. What are the questions, concerns about the pre-calc? Yes.
What do you mean the 2x is part of the product?
If you are to take the derivative of this, you have two things that are multiplied. So this is product rule. But when you get to the part when you have to take the derivative of this, that's when the chain rule will kick in. So that's going to be, we are not doing this yet. It's just understanding that not every single expression that you see that it's busy is automatically all function composition. This is the product part, and this is the chain function composition part. So not the whole thing is not composition. This part is a composition, this part is not. So that's just want to make sure that you guys are still seeing the products and quotients. It's not going to be 100%, but I did promise 95, so I'll deliver on the promise, as the future classes will as well. So let's do some chain rule, right? Let's have some fun over here. So chain rule formula. Chain rule formula is the derivative in terms of x of function composition is we take the outer function derivative with g still plugged in and then g of x in a chain. So this is your chain rule formula. This is what you are memorizing. And this is what you will be using. This formula is extremely, extremely important. It's going to get this very fancy border, as you can see.
Oh, so the 2x in the other one was just the f prime. Like in that formula?
No. This is not the derivative. This is me rewriting it. This same 2x is showing up. I just moved the 3 over here. This is not, I did not take any derivatives.
So you're going to find that using the product rule, once you found the derivative of the composed composition, then you're going to use the product rule with the differentiating the 2x.
It's the opposite, actually.
Okay.
We are doing the product, copy the first, and when you say derivative of the second, chain rule kicks in. Then copy the second, derivative of the first is just 2.
Right.
So that's what we're going to, but that's level 2. Let's first take it on level 1.
Okay.
So now, I have, let's go with this first example, the derivative of 3x plus 1 to the 5th power. If you like pain, go ahead, FOIL. I'll wait, right? But you would quickly say, all right, yeah, that was not fun. What do I do if the power is 50, right? So we do chain rule. And the chain rule goes this way. You can put some attitude to it if you want to, right? You can say, oh, that's the attitude, right? Oh, this problem would be so easy if it was just x to the 5. What's the derivative of x to the 5? It's 5x to the 4, right?
Yes.
So here, 5x to the 4. Now, my x is this 3x plus 1. So this is how you obtain the first part. Times the derivative of the inside is 3. And we're done. So the total is 15, 3x plus 1 to the 4th power. Let's take a look at the derivative of sine to the 8th power of x. You say, well, I can rewrite this as the derivative of sine x to the 8th power. And this is where you can go with the attitude. If this was just an x to the 8th power, this would be an easy problem, right? So what's the derivative of x to the 8? It's 8x to the 7. Now your x in this particular problem is sine x. So we put sine x there, and then times the chain. The derivative of sine is cosine x. Great. And that's the solution. That's done. So this part here is called the chain, right? The derivative of the inside. When I say the derivative of the inside, now is the time to take a look at the formula. Take a look at the examples. Please observe the answers. You have f prime, we have our 5x to the 4, but instead of x we put in g. See how g? That's your g. And look at the derivative of g, is 3. Right? Move to the next one. You have, again, function raised to the exponent, and then you have your 8 function g to the 7. Your g is sine, g prime is cosine. In my head as a student, I always went the derivative of the outside with g plugged in times the derivative of the inside. Why did I say inside? Because this g is always inside these parentheses. So the derivative of the inside. And that's stuck in my head. So it just works. If it doesn't work for you, move on, do something else, right? I learned the product rule. Derivative of the first, copy the first derivative of the second plus copy the second derivative of the first. That's how I learned it. I didn't go UV and primes and stuff like that. It was just saying it that way in my head, stuck, and I just went with it, right? So now, when I do the chain rule problems, I say, if all of this is a unit, I can regard that as x, which is actually g. So the derivative of that is 5x or g to the 4th, and that's exactly what I have here. And you keep this as g, and then its derivative goes there. Because we do have g prime as a chain. The derivative of cube root of 4x squared minus 1. This is the same problem as the two above. As soon as you rewrite this problem with the exponent 1/3, thank you. We don't care if the exponent is 1/3 or 8 or a 5. It's all the same, right? Drop it down, minus 1. So the derivative is 1/3, and then we have our g over here to the negative 2/3. So this is what I mean by the derivative of the outside. if this was to be a single variable x, you would take the derivative as 1/3 x to the negative 2/3 because you are subtracting 1. Are we all agreeing on that? Here's another example. The derivative of x to the 5 is 5x to the 4. So you drop the exponent down and you subtract 1. So I dropped the exponent down and I subtracted 1. Now for chain rule, our guts of the problem over here are not x's but g's. So this is 4x minus 1. And then for g prime, I follow with the derivative of the inside, right, which is 8x.
So you simplify that as 8/3 x?
Yes. So we will now simplify this with a fraction. We have a negative and we have x goes on top. So I have 8x on top. And I have 3 cube root of, open parenthesis, 4x squared minus 1 squared. Is this necessary to rewrite this way? Yes. Because how are we going to do this equal to 0? Right? Not fun. But if you do this equal to 0, hey, denominator dies right away, right? Because when you cross multiply, denominator multiplies into 0 and it's gone. So you just have 8x equals 0, x equals 0. So you can just solve it by looking at it.
Can you go to the denominator? Where'd you get the 3?
The 3, when you drop the exponent down, becomes 1/3, which is the 3.
And the other 3?
3 is the cube root from denominator of the fraction. I mean, denominator of the exponent. The derivative of cosine x to the 8th. What is the main function here?
X to the 8th.
Ooh, what, we're gonna go outside now?
That's right.
Or we can settle it civil. Is it x to the 8th or a cosine, right? So this is the story of, right, there is a difference between cosine 8x and cosine x to the 8th. They are not the same, right? So when your exponent is here on the left hand side, your main function f is x to the 8th and cosine is plugged in. On the other side, your main function is cosine x and x to the 8th is plugged in. So I need you to stare at this and write it down and understand that that holds for sine and tangent and ln. Same notation. So all 6 trig functions plus ln, they all have the same notation. So if this power is on the function of a cosine ln or something, then x to the 8th is the outer, and the function g is the cosine or ln or whatever. It swaps if you have, because of order of operations. This 8 is the exponent. There are no parentheses. Exponent is next, right? Exponent is on the function. Therefore, something to the 8 takes precedence. Where over here, 8 is directly impacting x only. And then cosine is impacting everything else. Now, when I was in high school, I remember struggle with this. It was, what's the name for the second year high school? Sophomore? Sophomore, thank you. I never learned those names, believe it or not. I just know that the senior is the last one, and the freshman is the first one, but the two in the middle, I can't sometimes even remember what's the third one, the name? Junior, thank you. Why is it the junior? Like, isn't the junior going?
The senior is a senior and junior is a junior.
Yeah, but what's the sophomore? Is it toddler? No, it's freshman? I don't know.
Almost,
Okay, whatever.
almost a sophomore, a junior.
Anyway, so the way I reasoned with this, so I don't get killed in the classroom, was what do I get to calculate first, right, if I had numbers? So that's how I figure things out. If this x was, let's say, pi, what would I be calculating first? Am I calculating something with the 8th exponent, or I'm calculating something with the cosine? So this is the way I, in my head, worked out which one gets to be the main function and which one gets to be the one that's plugged in. Because you will always start calculating at the bottom first. See, if x is equal to pi, I get to find cosine of pi first, and then raise that to the 8th power. In this situation, you see how 8 is glued to the x? If x is pi, you first get to do pi to the 8, and then hit it with a cosine. So that's the way I was decomposing when I was in high school, because it's tricky. It is tricky, especially if you don't have a lot of exposure to this. It is one lecture in your Pre-Calc 1 class, which for all of you is at least a year ago, right? And now I'm telling you that everything from this point on depends on you being able to do this like that. So I understand that it's going to take some time for you guys to kick in, right? But please spend insane amount of time on this, please, right? You are 2% here, welcome, right? But to push to the 1%, we need to take care of this, right? So if you are having trouble with visually which way it looks, go with this analogy. Okay, what would I calculate first? We can use that analogy, what would I calculate first, on previous examples as well. Take a square root example. If x is 3, are you computing the root first, or you're computing the expression of 4x squared minus 1, right? So you're computing the expression first. So if x is given to you to be, let's say, 3, then you have 35 over here. And then the cube root comes in. So remember what I did. I calculated the guts first, and then cube root came last. Which means whatever I calculate first, that's the inner function, because that one gets applied and calculated first. And then the outer one, which is broader, right, is the one that you calculate. Now, if that doesn't make you happy, let's flip the story. You have a bag, right? I have a bag. Bag is the outer function that you see. It is very simple to convert this bag into a parachute bag. I just stuff a parachute inside, right? I wouldn't recommend using it, but, right? So, the purpose of this bag is determined by its contents. You don't know what is in it, right? You're assuming that there are exams and labs, and right? Could be something else, right? Right? Could be 100K cash, right? You don't know. So technically what you are seeing from far away is this global big function, which is cube root, right? The guts of the bag, the contents of the bag, is what's inside of that outer function. So that's another way to understand which one is in, which one is out. You take the derivative of the one that is out first, and instead of writing x's, you plug in g everywhere, which is the inside, and then times the derivative of the inside. So it's very important to figure out which one is which. So going back to our cosine x to the 8, the derivative of cosine is negative sine, with the other function still plugged in, times the derivative of the inside. The derivative of the inside is x to the 8, so 8x to the 7. Giving us negative 8x to the 7 sine x to the 8 as the answer. Now, I have never seen any function in any application to look like this, right? This is gymnastics that we do because we can. Now, I immediately want to contrast this. I'm just going to move this down. I immediately want to contrast this with a problem in orange, the derivative of cosine to the 8x, which would be 8 cosine to the 7x times negative sine x, for a total of negative 8 sine x cosine to the 7x. Start these two examples, because this is where most of the confusion happens. This is where most of your grade dies on exams. Not getting the difference in notation between these two. So this 8 being on cosine or x is a vast difference, right, in what type of function you have. If you still don't believe me, go ahead eventually, right, tonight on Desmos, graph both of these functions and you will see that the lines are nothing alike. I'll leave this here as the explanation of why and how everything happened. All right, let's take a look at another example. The derivative of e raised to the x cubed plus 9x minus 1. If I say x is equal to 0, what is the first thing you're calculating? The polynomial or exponent? You are calculating polynomial first, therefore that's your g. And then you have your e to the x. Alright, so what's the derivative? The derivative of e is itself, so you get to copy the whole thing. And then times the chain rule, which is the derivative of the polynomial, 3x squared plus 9. Now, if you really want to be fancy, you kick 3 out, you have your x squared plus 3, and then e to the x cubed plus 9x minus 1.
No, I'm just going through it in my head and seeing if I'm ready to follow.
So that's the next step. So we are going to now go from 2 functions into 3 and 4, and then we're going to end the lecture with the cherry on top. We're tossing the product rule and quotient rule in the whole story. So we have to make sure first that the first step with the 2 functions, right, is clear. Which one goes where. So I'm going to ask you guys now to work out the derivative of e to the sine x. Yes.
How do you have exponents in exponents?
What do you mean exponents?
Like you have x raised to the 3rd power within the exponent for e.
Oh, you can string as much, because every function in the end is a number. So if I write x squared 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 squared, if I do this, right, it's okay, because if I put this as a 3 and I have a square and a square and a square and a square, I'm going to deal with this first, and I will get 9, and I will have these 2 squares. And I'm going to deal with this, get 81, and I still have these 2 squares. And I'm going to deal with this. You see how it goes? So you can string as many of these as you want. Mathematics puts no limitations, right? It's the application around us that governs what you get to use and what you get to keep for mathematical gymnastics, right? To flex, to show off, right? When someone says, what do you know? Look at this, right?
Is there like any like practical applications, like any real life situation where that would
this no, but you could run into stuff when it's nature is not complicated and too crazy with these kind of things. We tend to overthink a lot of stuff, so sure. The one that I'm saving one for later. So yes, we'll talk about one. You can have anything, because if I tell you that x is equal to 1, right? If I say x is equal to 1, this entire mess over here becomes 9. It is just e to the 9. And e to the 9, you punch in a calculator and you come up with a number. So we can have exponent within exponent, a function within a function, because ultimately all of these functions are numbers. Another thing, which I will also eventually talk in more detail, is that anytime you have this equation that you need to solve, you can completely look to that equation as just two graphs intersecting, and then if they intersect, you have a solution. I haven't seen anyone teach from that perspective, and a lot of that stuff gets to be lost, not understanding that the function eventually is actually equal to a y, and a y is on a y-axis a number, that it's from negative infinity to positive infinity, depending on what x you plug in. So I can literally put whatever I want, and I can just compute it, right? And I just follow the PEMDAS, and it will eventually work out. So we can have it. So what's my main function over here? Yes, so this is the one that you would see from the outside, and plugged in is sine x. So the derivative would be e to the sine x, because the derivative of e to the x is e to the x, so it's itself, times the derivative of sine is cosine x. Beautiful. So this is cosine x e to the sine x. Yeah, put parentheses if you want to. So that's that.
Is there a defined order for writing those cosine x, then e to the sine x, or
actually, I just when I wrote this, I saw that there was not preferred to be written this way.
Oh.
So that's why I put the parentheses. This one over here is better. So you caught me there.
No, by mistake though. I wonder how you know the order of. I mean, I know
It's-
in a polynomial, I can figure it out.
Yes, always the highest exponent for a polynomial. For these things, still in the example that I'm going to show later, we'll also address your question, but that's E and trig. Generally, polynomials in front of transcendental functions, which would be all of your ln's and e's and trigs. But it really doesn't matter as long as it's not bad to the point where you start confusing what goes where, which is the next example. I always have an example. How about, you all know what the derivative of tangent is, right? Good, because that's the next one. Tangent of e to the x. You see now, I'm turning the tables over here. So what's f?
10x.
10x, very good. And g would be e to the x. So the derivative of tangent is
Secant squared.
secant squared, and then we use e to the x, right, as its argument, times the derivative of e to the x is e to the x, and this is where we would put e to the x first, and then we have secant squared of e to the x.
Isn't the same thing when you say secant e to the 2x? Is that the same thing?
No, because this, we have a very important question. Is this the same as secant e to the 2x? So this e to the x here is buried within the secant, and this one over here is free. So this one can jump in front. The second one stays buried. When I say buried, that means that when you have a trigonometric function, say sine, you must put something over here. Because, let me just ask you, is this mathematical term? No. What is this? It's a religious term. This has nothing to do with mathematics. If you write it like this, it has nothing to do with mathematics. What is this?
It's a thing you burn.
It's a thing you burn. Yes, it's a log. It looks like that, right? As the branch there, right? That's what it is. It's a log. All right. See, these functions that contain letters, you have to follow with some kind of what we call an argument. So if you just go and you write secant squared and you walk away, it's as weird as if you would just please do this once in your lifetime. Just walk up to a random person somewhere, anywhere, on a train station, anywhere, and just say 4, and you just leave. That's exactly what it is. Just say, or say 5 or whatever number, doesn't matter. Just say a number and leave. I make sure it's nowhere close to what the time is, or a date or something. You know, just walk away. It's tons of fun, actually. So you will always have for the full trig function and notation, you must have the argument following. So it's sine of x, it's log of x, or x squared, or something. So something must be there. You don't get to write them without, because they are no longer mathematical terms, right? And then the other ones are even worse, because this has no meaning whatsoever if you just put it down, right, and you walk. So that's that. And so this e to the x is buried because it's the argument of secant, and this e to the x is its own function, which is why we are allowed to put it in front. Now, remember the notation when I said earlier in class and times before that sine squared x you can also write as sine x everything squared. So this secant that you have here can be written as secant of e to the x, where e to the x is the argument, everything squared. So you can see it that way as well. But this e to the x is the argument of the function secant. Green?
So you could write it that way as well, and be correct?
Yes. So whatever makes you guys happy in terms of notation is just notation has to be followed because this is universal language. I always have this story that my friend used to work in Germany for 2 years. He had an awful job. He was a control engineer for a company that was working on air conditioning for cars, air conditioning units. So his job was to drive prototype German cars, so the next year or 2 years ahead models, from Germany to Italy and back to test the air conditioning and all of the electronics and everything they have. Now these prototype cars from Germany include what? Mercedes, good. What else? BMW, yes, what else? Audi, yes, what else? Porsche, yes, what else? So he had to drive. It's a poor thing, right? These prototype cars that are not even out, you know, talking about Audi S5 or S7. And the crazy thing about it is that you have to drive it on a highway that has no speed limit. That was another, yeah. So it was tough. I mean, the 2 years he spent over there. Now, as engineer, the only language you have to communicate with Germans, since you are Serbian, right, is mathematics. So if they don't have the common notation and they don't understand each other's equations. So it's a problem, right? I know. It's tough. I said, you graduate and then you get a job and then you just suffer. It's just misery after that. All right. Let's do an example from the homework and then move to 3 variables as per request. Oh, perfect. I mean, problem 44. They just know what's up. Look at this. The derivative of, who came up with this? Sine of 4 cosine x. Beautiful. Excellent. That's your problem 44. What is my outer function?
Sine x.
Thank you. So f is going to be sine x, and that's the first one we are taking the derivative of. And how about the inner one? 4 cosine x. Very good. So we are going to take the derivative of the outer function. So sine derivative of that would be cosine of 4 cosine x. Remember that you have to keep the guts as is. Times the derivative of the inside is negative 4 sine x. Yes. So in this case, we are going to kick negative 4 sine x in front and then multiply that by cosine cosine of 4 cosine x. Beautiful. We're going to, yes? No, 4 is glued, so it's, you copy 4. Right? If you are taking the derivative of 4 cosine x, you will copy the 4 and then you will have negative sine x in a derivative. So 4 gets copied. It's a constant. Now we're going to do multiple, and then we're going to take the break. When we come back, we'll do the product rule, quotient rule in conjunction with this. So we're going to do it in two parts. So the next, this is like a subtitle. More than two functions. That's the subtitle. I know it's a bad title, but you know exactly what I'm talking about. Now what I'm going to do is I'm going to put the derivative of f of g of h of x. So I have a triple case. Now this is going to be the derivative of f with g of h of x still plugged in, times the derivative of g with h still plugged in, and finally times the derivative of h. So please look at the pattern. 1, 2, 3, 1, 2, 3. 3 functions, 3 3 factors in a product. 1, 2, 3, 1, 2, 3. That's what it is. If I put 5 functions nested, I will have 5 of these. The best example, the one that shows up most often, would be the derivative of sine squared of x cubed, let's say. So now we need to untangle this and figure out what's f, what's g, what's h. We do see a couple of different functions there. And it would be helpful if you rewrite this using the parenthesis, so we have sine x cubed and then everything squared, because that definitely helps with figuring out what is the most outer function. So what's my f? X squared, very good. What's g, one in? Sine x. And then h, x cubed. Decomposing these, again, guys, this is a skill that can be learned, all right? Time, patience, right? And you get there. We are not born, no one is born knowing this. It's just discipline and time and willingness to do it. You look at, when you decompose, try to put it back together. And you always start on the bottom, plug in the one above. So when you plug in x cubed into sine x, you get sine x cubed. And you plug in sine x cubed into x squared, you get sine squared x cubed. Great, it works. So now what's the derivative? The derivative of x squared. So that's the derivative of this. Remember, the whole thing here, sine x cubed, is now guts, right? So we have 2 something to the first power, and that something is sine x cubed, times the derivative of the inside. Well, the derivative of sine is cosine x cubed, times the derivative of x cubed is 3x squared. Now, before someone asks me, how do I know? I'm going to erase this one. It looks like a prime. It's not a prime. I erased the one. Usually students ask, how do I know when to stop? Because I can still take the derivative of 3x squared, get 6x, and then the next one is a 6, and the derivative of 6 is 0. Hey, each derivative is 0 now, right? No. Remember when I said 1, 2, 3? Well, 1, 2, 3, and you stop. If you have 4, 1, 2, 3, 4, stop. They're not going to work to be 0. What's the derivative? What is the function that will yield the derivative of 0? Constant, right? So you don't get to beat this up until it's 0 at the end, right? So if you see 3 functions, it's 1, 2, 3 levels, stop. I understand that if you keep going, it will eventually get 0, but stop. So we always had, in all of the previous examples, we always had 2, because we always had f and g. In this example, we have f, g, h, 3, so 1, 2, 3, stop. Let's take a look at problem 53. So we'll do 2 more examples and then the break. The derivative of sine of e to the x.
Professor, one question about the last question you just did. Is that how it's written in its final form, I guess?
No. We still have to write it as a 6x squared and then all of these things.
Okay.
Ooh, actually, you can be very fancy with this. Huh. You can be very fancy with this problem, with this answer. Because look what you have. 2 sine cosine. That's a double angle in identities. Oh, my Calc 2 would love this. Poor souls to see their calculations with trig. One of the students says, at this point I'm just copying, not even processing. I was like, wow. All right, so 2 sine cosine is going to turn into sine of 2x cubed, doubling the angle. I need to put 3x squared in front. So 3x squared first, followed by the orange sine 2x cubed. And I'm going to write the formula on the side that sine 2x is 2 sine x cosine x, for those of you who don't remember this identity. So this would be the coolest answer.
Is the less cool answer correct still?
Yes, it is. But this is the boss level,
Yeah.
you know? The boss level. What is my F over here?
Sine X.
Okay, how about G?
Sine X.
Oh. And how about H? X. Good. Thank you. So the derivative of sine is cosine with sine e to the x plugged in, times the derivative of the inside is a cosine of e to the x, times the derivative of e to the x is itself. So now, e to the x, cosine e to the x, cosine of sine e to the x. Okay, one more example and we'll take a break I don't want you to overheat. Already too late? Okay. I'm going, are we ready for this? Are we ready for this? Let's see. 59. The derivative of, I'm just seeing how close the door is. I'm gonna make a run for it. Square root of x plus root x. Bye. I'll be right back. I will rewrite this as x plus x to 1/2, everything to 1/2. And from that point, it should be easy, right? We hope. We have something, remember? Something raised to a 1/2 power. So act on it. 1/2 of that something to the negative 1/2. And that something is x plus x to the 1/2. Times the derivative of the inside, which is 1 plus 1/2 x to the negative 1/2. That's it. I hope you're not disappointed. Now you can make it pretty by placing all these square roots. This is denominator, yeah, so we have a 2 square root of x plus square root of x, 1 plus 1 over 2 root x, and now we multiply to fix this. Well, because you do 2 root x on both. Yes, to double fraction. So I have 2 root x plus 1, right? The first one multiplies, the second one cancels. Divided by 2 times 2 is 4. And under the radical, this becomes x squared plus x root x. It's terrible. But that's called mathematical gymnastics, right? You know, casually leave this on a napkin as you leave the restaurant. I did that every time we went to Disney last summer, and at the hotel, I left something like this from Calc 3 every single morning. Just wanted to see what's going to happen next time, who's going to be. It's a lot of fun. All right, well, this is part 1. When we come back, we'll do more. Yes?
So, how do we know it's this 2 in this one, like 2 function? Because
you have a square root within the square root, right? Square root of x is a function.
so once it's the like plus, like the what we consider as g, it's a function. It's an addition function. We cannot take under root x or the third one.
No.
No.
Because the addition, you apply derivative to each, right? Addition, that it's 2 separate derivatives, which is exactly why I picked this problem, because it looks so weird. The next one is worse, because it has 3 of these x's, and you should practice. The problem 60, try it, homework. It's the same, just add another root x. So it's, you know, there's going to be 3 of them. All right. Take a break, and we're coming back with vengeance.